Today I'm going to tell you about some of the work that I've been doing along with my group, my students, and many other people. And this is what's going on with measuring properties of muons and kaons. Let me start off by stealing a statement from the mission statement from DOE, which is, what is it that we're doing with high energy physics? Well, the goal is to simply understand how the universe works. And we do this by discovering the most elementary constituents of matter and probing their interactions, and even exploring the nature of time and space itself. So this study of the fundamental constituents of matter is what we are going to talk about today. So what is a muon and what is a kaon? A kaon is a, let's see if this mouse works. Kaon is a meson. And like all mesons, it's made of two particles, a quark and an antiquark. So you take any one of these quarks listed here, UCT, DSB, and you pair it with an antiversion of one of these quarks, an anti-U or an anti-C or an anti-S, which we note with a bar over the quark. So a K0 is a D and an S bar, this quark, and an antiversion of this. A K0 bar is just the opposite, antiversion of this, and an SK plus, we take this one, and a K minus, we take the antiversion of this one. A muon, on the other hand, is itself a fundamental particle. It's not made of any other particles. It's showing up right here and is essentially a heavy version of the electron. So how can these little particles help us understand, help us answer these big questions? So that sort of goes a little bit into philosophy. And what I want to do next is trace out, how does this sequence of things, how do these simple experiments, these simple observations tell us a big story? And I'm going to start at the beginning. I'm going to start with Galileo. He was really the first one to write down this particular method of understanding nature. And this is from a book that he wrote called Two New Sciences. When he wrote this book, he was already under house arrest. And this was published in 1638. It shows up down here in Roman numerals. And one of the things that he said in this book is, take a piece of wooden molding, like we have here, and take it about 12 cubits long. Well, I don't exactly know how long a cubit is, but I did get a 2x4x8, which is probably okay. It's about a cubit wide and 3 finger breadths thick. Well, that's about right. And make a groove in it. So I have this groove in it, and then polish it and line it with parchment. We didn't have parchment, but we used varnish instead. Make it smooth and polished, and then take a bronze ball. We have a steel ball instead, and let it roll down this. What you're supposed to notice isn't by watching it, it's by listening to it. I'm going to do it again, and just listen to the clicks as it goes along. Because we put little wires over the channel, so when the steel ball rolls over the wire, it makes a click. And what you noticed, just by your own sense of timing, was those clicks were equal time intervals. And Galileo's mechanism for understanding or measuring time was his own sense of rhythm. He was trained as a musician on the violin, so just his own sense of rhythm. And other times he used to measure longer times by just using his heartbeat and counting the number of pulses. So you see in his writings, whenever he talks about time durations, he always talks about it in terms of heartbeats. How many heartbeats was this? So from this very simple experiment, he came up with this description. Not only did he make the observation, but he also made a mathematical model. Now, Galileo's methods for analysis, the tools that he used for analysis, was two things: a straight edge and a compass. He did everything in geometry with just straight lines, equal tick marks along the lines, and circles when he needed a circle. He didn't say, for example, acceleration is 1/2 gt squared. He didn't have that language. The equal sign had not yet been invented when Galileo did his work. So what he has here is this line here, which represents distances. And in the first tick, it goes this far, one space. In the second tick, it's gone 3 more. By the third tick, it's gone 5 more. By the next tick, it's gone 7 more. So this sequence of 1, 3, 5, 7, as many of you know, if you take the sum of these, 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, you get this series of perfect squares. So the spaces described by a body falling from rest with a uniformly accelerated motion are to each other as the squares of the time intervals. This is again from his book. He wrote this after he was already in house arrest, accumulating in this book almost all of his work. And another quote that I liked from his textbook was along the lines, if these other guys were so smart, Archimedes, Apollonius, Euclid, why didn't they think of this? Okay? And so he's speaking, in the style of his writing, he's speaking as a third person. The academician, of course, is Galileo himself. If he can do all of these things, observing by watching nature and making these discoveries and making all these proofs, then what were these guys up to, and why should we pay any more attention to them? This was one of Galileo's. He was never really accused of being overly modest. But one of his faults was he was not hesitant in speaking truth to power, truth to authority. And that got him in some trouble. Okay. But what he did was establish this principle that you can see a lot just by looking. And you can, from making these observations, you can make mathematical models that accurately describe nature. So now I want to skip ahead 175 years to a next really important observation. And this was done by Michael Faraday around 1813, 1814. And Michael Faraday was was experimenting with magnets and wires and charging them up and using batteries. And he did an experiment like this, where he takes a coil, like I have here, but instead of a battery, I'm going to use a power supply plugged into the wall. And this power supply is AC. So it's going to point this way, and then it's going to point this way, making a magnetic field going up and down, switching at 60 hertz. And now if we take, as he has, a second coil and wrap around this first coil, well, nothing yet. Maybe people in the first row can see this light bulb is lighting up a little bit. Now you should see it more. As we do more and more turns, the light bulb is getting brighter. And so Faraday discovered this effect, that a changing magnetic field can make a current. And if you take more and more windings, you get more and more current. And if we take this with a lot of windings in it, with 3 light bulbs, then we can make this one light up. And if there's no strings attached here. Okay. Okay, it's just the magnetic field going through. And then if we take even more, we have a 100-watt light bulb there, which we can make light up with this. Okay. Now, after Faraday did this, the Royal Institution where he was working said, well, that's all nice and pretty, but we don't see any practical application of what you're doing. And the problem that we really need you to work on is using your knowledge of chemistry to make glass clearer. Because, you know, when we make glass now, there's impurities in it, it gets cloudy. How can we fix it so the glass comes out much clearer? Okay, so he had to work on making glass clearer for 7 years. Finally, he was done with that project and got to come back to what he was doing with electricity and magnetism. And one of the things that he did was, let me go to the next slide, was to take this, I'm going to use a laser pointer, this cup of mercury connected to the 2 sides of a battery and a wire hanging down with a magnet coming up through the mercury. We have a model of that, except we're using salt water instead of mercury. And if we connect it to the battery, what we see is this example of continuous motion coming from electricity and magnetism. Very first time in 1821 that this had been observed. There were some theories of what should happen if you have a wire near a magnet. And that theory was put forward by Wollaston, who said the wire should just turn on its own axis. It shouldn't go around like this. Consequently, when Faraday published his essentially the invention of the electric motor, rather than being allowed to continue to work on it, Wollaston, who had the theory that the wire should rotate on its own axis, basically kept him out of being a full member of the Royal Society. And he was again asked to work on something else. Another example of, at that time, the consequence of speaking truth to authority. So let's go on to the next topic I want to talk about. So from Faraday's experiments, a new understanding of electricity and magnetism emerged. And by the end of the 1800s, Maxwell was able to capture all of this understanding. An essential part was that a changing magnetic field gives an electric field into a set of equations known as Maxwell's equations. By 1884, John Henry Poynting, who was at I just slipped my mind where he was from. It wasn't Oxford or Cambridge. Okay. Came up with a theory about how energy is transported by electric and magnetic fields. Now, you can verify this yourself by just going outside on a sunny day and face the sun. And you will feel the sunlight on your cheeks. You will feel this energy being transported from the sun to you. And it is proportional to the strength of the electric field and the strength of the magnetic field. And this energy per area, per second, watts per area, is proportional to just these. It does not depend on frequency. The amount of energy transported is independent of the frequency. Just the intensity is all that matters. So then there was another effect which was observed. And let's see. Which was, here we go. So here I have a zinc plate, and here is a device which tells us how much charge is on this zinc plate. So I can take this and charge the plate up. And there you see the needle on the electroscope has moved. And that charge is just staying there. Now, even though it's in this intense light. So I would expect from Poynting's equation, the light that's coming from these lamps to discharge this plate. But it turns out that no matter how intense that light is, it doesn't discharge it. But if I take a ultraviolet, and you can see this perhaps as a blue light, and I expose this to blue light, then the charge immediately goes away. And so this is now in violation of the electromagnetic theory that was developed by Maxwell. And it took someone else in 1905 to explain what was going on. And that is that it's not just the total energy that's being transmitted by the electromagnetic waves. It also depends on the frequency. And this, of course, introduced the idea of quantum mechanics. Now, things had also changed between Galileo and Faraday and Einstein, and instead of Einstein being punished for making this discovery, he was awarded the Nobel Prize. Okay. So things are getting better. Okay, so simple things, the point of all of these demos, the simple things can really tell us a lot about how nature works. A ball rolling down an inclined plane, two coils of wire putting together a magnet, and just the charge on a plate being discharged depending on the frequency of the light. So now I want to come to the last demo that I have. From all of these experiments, in particular Rutherford's scattering of alpha particles off of thin foils, a model of the atom emerged. And this model had a nucleus consisting of protons and neutrons at the center and electrons going around these, the nucleus. The size of the atom, the outer dimensions of the electrons, about 10 to the minus 10th meters, and the nucleus about 10 to the minus 15th meters. That is, the nucleus is 10,000 times smaller than the atoms themselves. Moreover, the nucleus is consisted of protons that are attracted to each other. But protons have the same charge. They're both positive. And we know that two things of the same sign repel each other. So these protons should be repelling each other through the Coulomb interaction. But yet they're stuck together. So there must be a force stronger than the electric force that only acts over short distances. And physicists, using the full power of their imagination, called this new force that was stronger than the electric force the strong force. Okay. And it's still known as that today. Acts over only short distances. Yukawa came up with a theory that could explain this. That instead of the potential falling like 1 over r, the potential fell like 1 over r with an exponential term in it. And this exponential term had the mass of the particle that was exchanged in the force. This was something that was carrying the force. In the case of the Coulomb force, the mass of this is the photon, which is 0. And so if you make this e to the 0, you get this equation back. So Yukawa came up with this nice theory that could explain this interaction. He made this prediction in 1935, and then 2 years later, Anderson and Niedermeyer discovered a particle that was almost exactly the right mass to be this particle that held the nucleus together. 1941, Piccioni and Conversi decided they were going to work together and measure the lifetime of this mesotron. Now, one of the things they had to do was to develop a new circuit to do this. These are vacuum tubes. This is before transistors, okay? And there was nothing available to do this kind of measurement. Now, at the time, vacuum tubes were being used to measure these kinds of particles. And these amplifiers in these vacuum tubes were so difficult to use because they would either do one of two things. They would oscillate or they wouldn't work at all. And getting them to work was sort of like setting a pencil on its tip. It just had to stay there. Fermi said getting these circuits to work was so difficult that if you needed 2 of them together, that would be really, really hard. And 3 of them all working at the same time would be impossible. And they needed 4 of them all working at the same time. So another theme is, this is a job for optimists. If you pay attention to what the experts are saying, they will say, this will never work. Why are you even bothering to try? In 1941, Piccioni and Conversi put together this kind of experiment. We have a model of this part of their experiment. Go to the next slide. There we go. So let me talk about what's going on here. We have a detector here, which when a charged particle goes through it, gives a little flash of light. That flash of light is picked up by a phototube, which then goes to an amplifier. If that same particle keeps coming down and goes through this one as well, then we get, this is from the first phototube, this is from the second phototube. This is when there is a coincidence between them. And this circuit that Conversi put together was basically to measure this coincidence. Except they also had a big chunk of steel that was magnetized, multiples of these, this making a coincidence of 3 of these, and this making a coincidence of 4. The magnetized steel was to bend mu minuses one way and the positive particles the other way. They would then come down and be trapped in this absorber where they would decay. The goal of this was to measure how long these particles live before they decay. And the answer is it's about 1/millionth of a second. So this was a difficult measurement to make. The difficulty was compounded by what was going on at Rome in the 1940s. Bombs were falling outside. So in addition to this problem with this electronic circuit, they had to worry about the windows being blown out and destroying the equipment. So they lined their windows with sandbags. The person who was working on this electronics, expert in vacuum tube electronics, also was helping the resistance with maintaining their radios so they could communicate with each other during the Nazi occupation. And so every day they wondered, as their technician went outside at night after curfew, was he going to come back in the morning? So you have to be an optimist to do these kinds of things. So the result from this came out, they started in 1941, came out in 1947. Oops, let me go back one. And notice the date here. This was published February 1st, 1947, this result. This mesotron cannot be the Yukawa particle, was the conclusion of this, published by Fermi, Teller, and Weisskopf. And note the date by which this conclusion was received by the journal, 6 days later. So this paper came out, and Fermi and Teller say, well, if its lifetime is 10 to the minus 6 seconds, it can't be the Yukawa particle, because we think the estimate for that lifetime would be 12 orders of magnitude shorter. Okay? So this one experiment on muons told us a lot about what's going on with the structure of the atom, and gave us this idea, and consequently this mesotron, which was the particle being looked at then, was renamed the muon. So back to where I started on this, what can these little particles tell us about nature? A lot, okay? And you have to combine experimental measurements with a theoretical understanding, and the experimental measurements is what guides the theoretical understanding. So we're going to be looking at 2 of these little particles, kaons and muons. And what we're looking for is a kaon going to a pi 0 and 2 neutrinos, and the muon just turning into an electron. Why are these important? Because in our current understanding of physics, these processes can't happen, or can happen at a very low rate. And if we see them at a higher rate than is predicted, there must be something else in our models. This is the standard model of particle physics, consisting again of quarks and leptons. Here are the quarks up here. Here are the leptons down here. And these are the force carriers. This is what carries the strong force. And because it is needed to glue these protons together in the nucleus, this force carrier is called the gluon. Okay? And the photon carries light. These 3 particles are responsible for radioactive decay, and the Higgs is responsible for mass. This particle, the Higgs, neutral. The Z is neutral. The photon is neutral. Gluon is neutral. Consequently, when they interact with these particles, they must interact with a particle and its antiparticle pair. So Higgs, photon, Z can interact with a muon and an anti-muon, or an electron and an anti-electron, or an up quark and not an up quark. That is, this particle, this particle, this particle, and this particle can't go between any of these. Only the particle and its antiparticle. The ones that can go between are these W's. And they operate on pairs, either electron and this neutrino, muon and this neutrino, tau and this neutrino, or this pair of quarks, this pair of quarks, and this pair of quarks. There's nothing that can change quarks along this line, or change these kinds of, change from quarks to here, okay? So the S quark can't change into a D quark. That would be going sideways in that diagram. So consequently, the K long going to a pi 0, this is the Kaon, this is the pion, changing an S into a D can't happen directly. We can go up, we can go from a strange quark into one of the other ones, a U or a C or a T, by emitting a W. Then that U or C or T, after having traveled 10 to the minus 18th meters, can interact with the W again and turn back into a D. And if during this very short time of existence for these, they can emit a Z particle, that can decay into 2 neutrinos. So our final state is pion and 2 neutrinos. But this happens much less than the other kinds of way that a kaon can decay. So if we calculate how many times it will go this way, it should be 1 out of 3 times 10 to the 12 kaons. So we need lots of kaons. We need billions and billions and billions, 1,000 billion kaons. Here's what the branching ratio is for the other ways the kaon decays. So we need to look at a lot of them. And these kaons only live for 5 times 10 to the minus 8 seconds. That's not very long, so you better look quick. Now, in the perverse worldview of particle physicists, a particle that lives for 10, 5, 15 nanoseconds, it's called a stable particle. Okay. This is one of the stable particles. We can actually make beams out of these particles. And there's 3 places in the world that you can make kaons. CERN near Geneva, Switzerland, Fermilab near Chicago, and J-Park in Tokai, Japan. And it turns out J-Park is the place that can make the most of them per second. Okay. So where is this experiment that is looking for this decay? It's here in Japan, at Tokai. And this is a picture of the Accelerator Campus. This is the beach along the Pacific Ocean here. And this is the first stage of acceleration, a LINAC. Second stage is a rapid cycling cyclotron. So the particles start here, go down to here, get sped up. Then they go into this ring, get sped up even more. Then they're taken out and go into the Hadron Hall here, which is where our experiment is. And inside Hadron Hall, we have this beam of primary protons coming along. They strike a gold rod and produce many other short-lived particles. And we look at an angle of 16 degrees from here, run these particles through a magnetic field that takes the charged particles away. Here's where the target is. Here are the magnets. And what's left is particles that aren't charged that come down and go into our detector. We get all of the stable charged particles. Photons, neutrons, which I usually refer to as the evil neutrons, and Kaons. These neutrons are the major source of our background. So this is a schematic side view of our detector. The kaons, along with their photons and the evil neutrons, come in, and either the kaons decay in this region or they keep on going. The photons and neutrons also keep going. And when they decay in here, we're looking for the pion to produce 2 photons inside this calorimeter here. So we need a beam of kaons, need to efficiently detect when this happens, and we need to reject those other 100 billion kaons that are coming in here and decaying. So what we have is, this is our detector for the signal, and surrounding this is the detector to eliminate all of these other backgrounds coming in. You have to be an optimist to want to do this. This is a picture of Stephanie, one of our graduate students, working on the electronics that receives. Remember, Conversely had to make 4 of these channels work. We have to make 4,000 of these channels working all at the same time. This is just the cable plant coming from the detector into the electronics. And this is Stephanie standing in the center of our detector to give you a sense of scale. This is one of the detectors that is used to eliminate the background. Once we've collected this data, we have to do an analysis. We do what's called a blind analysis. That is, we don't look at the data until we have all of our analysis tools in place, because we don't want to be fooled by looking at the data and making our analysis choices based on what the data is telling us. We have to reconstruct the signal events, the 2 photons from the pi 0, using just the photon position and energy. We need to know how many other kaons came in to this detector, because we're looking at the ratio of the total number of kaons coming in to the ones that decay in the signal region. And we need to estimate how many different ways we can get fooled into thinking we have a signal event when in fact we don't. This is our first result from our first 100 hours of taking data. The axes here are, this is the distance along the detector. So this is coming into the detector, going through the vacuum, and getting to where our cesium iodide photodetectors are. This axis tells us how much momentum the photon the pi 0 has to the side. As the kaon is going along, it decays. 2 neutrinos go this way. The pi 0 goes up. And what distinguishes our signal from background is this pi 0 going away from the neutrinos. So this is our signal region. We look for events to be in here to say this is the signal. This is background caused by interactions at the front of the detector. This is another decay mode, making pi 0s where we miss the pi plus and the pi minus. But that pi 0 can't quite get as much momentum going up because these two particles are much heavier than the neutrinos. And what we make is estimates for each of these different regions in this plot of how many events should be there. And when we looked, we saw one. And remember, this is a job for optimists. When we saw that one, and we were setting a limit at 10 to the minus 8, we were still a factor of 1,000 away. And so that was a moment of profound disappointment. So we had to work on what are we going to do, because just extrapolating, this took 7 years, and I don't know of any graduate student who has this much patience. So we're going to have to find something else to do. And the pessimist out in the community said, "We told you so." But nevertheless, we're going to keep working on this. So we need to suppress these evil neutrons by improving the collimator, replacing the vacuum window with a thinner one, and in addition, purposely taking events with these neutrons so we can understand what they look like and distinguish them from photons. Put in additional detectors and increase the beam intensity. So last summer we looked at some additional data being taken. This is from the 2015 data, about an order of magnitude better in the limit that we're going to do because we've accumulated so much additional data. Again, we have this plot. This is position. This is the momentum. These are how many background events we expect in each of these regions. And there's a few less down here, even though we have roughly a factor of 400 more data. And this is the region that we aren't allowed to look at until we have completed all of our analysis tools. Then we look. And we were so happy to see this number, even though it was all that work for nothing. We were still really happy about that. So this set us a new limit, 3 times 10 to the minus 9. We're now, remember the standard model branching ratio is about 3 times 10 to the minus 11. So now it's only 700 years to get to the next limit. But we have some more tricks that we can do. Continue to increase the beam power so we get more kaons. Improve the neutron rejection by detector improvements. Improve the analysis techniques. And by now, our expectation is by 2025, we should get to the limit. Now I want to turn my attention to the muons. I don't want them to feel left out. So this idea of muons, this concept of lepton number conservation, has been around for a long time. For example, in neutron decay, a neutron goes to a proton, an electron, and an antineutrino. The number of leptons on this side, 0, is the same as the number on this side, 0. It was then discovered that the electron lepton number and the muon lepton number separately need to be conserved. That is, in a muon decaying to an electron kind of neutrino, and a muon kind of neutrino, that overall the leptons have to be the same on both sides of the equation, but also the number of electron-type leptons and the number of muon-type leptons also have to be conserved. And going back to our picture of the standard model again, we have up, down, charm, strange, top, bottom, the 3 leptons and their 3 charged electrons and their neutrinos. The weak interaction can interact, this is the W, can interact with any of these pairs, like so. In addition, the weak interaction can go across pairs, so we can connect to an S and a U. And that's how we see this S to D transition in the kaons. The S goes first to one of these, and then in turn comes back down to the D quark. Leptons can't do that. So while it's allowed for the quarks, it's forbidden for leptons. So a Z connecting to a muon and electron, not allowed. Can't do that. Can't turn a muon into an electron this way. However, you can do the same kind of trick by, first of all, taking this muon-type neutrino, and we now know that because of the finite mass of the neutrinos that they mix. So this neutrino comes over here, mixes, becomes an electron neutrino. Now, in the past, the distance over which we've had to see this kind of mixing of neutrinos has been hundreds or thousands of kilometers. And for this to happen, it has to happen inside the size of a nucleus, 10 to the minus 18 meters. 10 to the minus 18 is a lot smaller than 10 to the 6. So this can't happen very often. Calculations, I've seen both 10 to the minus 50 on the low end, 10 to the minus 54 on the high end. This is a tiny number. Even the most optimistic among us wouldn't try to do this, because it would require taking the entire mass of the Earth and converting it into muons and watching them all decay and seeing the one that didn't decay this way. Okay. So probably not going to do this measurement. But there still is lots of room to observe something, because in models of nature that go beyond the standard model to solve some particular problems, like why does the universe exist? Why is there only matter in the universe, not an equal amount of matter and antimatter? We have to put in some level of charged lepton flavor violation to see this. So it's a way of looking for processes that very rarely happen. And any observation of this would lead to new models of physics. So how does this muon to electron inversion happen? We have to put the muon very near a nucleus, just as Conversi and Pecciani did, having it captured onto, they captured it either onto carbon or iron. The electron being negatively charged, the muon being negatively charged is attracted to the nucleus, and once it gets close, it can interact with the nucleus. So when it's captured, and it gets captured pretty fast, 10 to the minus 10 seconds, roughly, can interact this way. And the reaction is against the nucleus as a whole, and that absorbs the momentum from the muon decaying, and the electron that comes out with the entire energy of the muon. So we see this electron coming out with 105 MeV. Other experiments were done looking for the muon to decay into electron and photon in free space. That had some nasty backgrounds. So the relative rate of these also can tell us more about what is going on, since this interaction of the muon with the nucleus can occur by other things than photons. Been searching for this for a long time. Here's the year going by, and here is the fraction of muons that can turn into electrons, starting around 1 in 10 back in late 1940s, and coming down now to around 10 to the minus 12. Note this particular limit. Our friend the K0, can it decay into just a muon and an electron? That would also violate this lepton number conservation, and it has some of the best limits out here. Here's where we want to go. Here's where all of the efforts to date have landed. You got to be an optimist to want to get down to this far. So how do we do this? Well, we're going to take some protons in, make some muons. Actually, we don't make muons, we make pions. Pions then decay to muons. Take those muons and look for them to turn into electrons. Then we do it again. And we keep doing this every 1.5 microseconds for 10 years. And we need to design a transport channel to capture these guys and transport the right sign. Conversely, Impaccioni did this with the magnetized steel. Low momentum muons from the production target where they're made to the capture target where they land on this aluminum. And make a detector that captures this electron from all of the other electrons. So we have this muon bunch, this bunch of muons going along at roughly the speed of light, and it sees these thin sheets of aluminum. Some of the muons get captured onto the aluminum nucleus and go down. And this muon bunch keeps going. And then we look for an electron just popping out of here. And meanwhile, this muon bunch has gone down, and we don't want any other muons coming in at the same time as we're looking for this electron. So how do we do this? Well, first of all, we bring in a beam of protons into what's called a production target. And here we make pions. The pions then come out and they spiral in this magnetic field, but this magnetic field is getting stronger as you go this way. So these pions are spiraling in the magnetic field, but the magnetic field's getting stronger and it pushes them back. So they spiral, come back out. Then the pions go into this pipe where they turn into muons. Then the muons come down here, hit this piece of aluminum. They stop. Now we've got to turn this whole thing off. Wait a few nanoseconds. Then look for an electron to pop out. That electron pops out and goes into our detector here. So this shows the protons coming in, and that's during this pulse. Then we wait, another pulse comes along. After the proton hits it, this pion pops out and gets repelled by the magnetic field, goes down this pipe, and the resulting muon stops in the target. For every proton that goes in, we get 0.0025 muons coming out. So we need a lot of protons coming in. Once the muon stops, the electron pops out, spirals around in its magnetic field, and then goes through our detectors. So this production target, we have the proton beam coming in with 50 kilowatts of protons coming in, and we have it surrounded by this superconducting coil. These superconducting magnets have to work at a fraction of a degree Kelvin, so you don't want any heat to go into that. As we talk to the magnet designers, and they say, you're going to put what into the center of this? You're going to put 50 kilowatts of heat into the center of this superconducting magnet? Well, that will never work. But you got to be an optimist. So we design all of these to basically be heat shields to deflect this heat away. Now this has to be in vacuum. And one of the things that you can't put in vacuum is any cooling. I can't tell you how many hours I've spent in meetings where we talk about you can't have cooling, but you've got to have cooling. You can't have cooling. Then the pions spiral out into the production, to the transport solenoid. Now we have this S-shaped solenoid. First one like this has ever been built. And pions spiral along. If they aren't the kind that we need, they hit this piece of steel here. Then the muons come out and go along into the next section. Muons come in, hit this stopping target. Then we have to stop any other particles from coming in because we want to look for these electrons popping out. This is the magnetic field during this whole process, the production solenoid with its steep gradient, so that when the pions are made, they get reflected back down, go down this way. Here's where the muons come along, go into the detector. Been working on this since 1992. And we expect first beam in 2021, getting really close. But consequently, I don't have any results to show you since we haven't yet started taking data. We're in the process of putting this whole thing together. So we have this experiment where we propose to measure this ratio to 2 times 10 to the minus 17. The Kaon experiment where we were going to 2 times 10 to the minus 11 wasn't hard enough. I need something that's 1,000,000 times harder. Okay. Any signal we see here will be indication of new physics. In addition, we are already starting on upgrading this experiment, making a new version, even though the current one's not done, and trying to get down to 10 to the minus 19 eventually. Okay. Even the absence of a signal will be useful for putting a constraint on ideas that theorists are having. So, to wrap up, we're continuing this process, started from just a ball rolling down an inclined plane, of using observations of nature to tell us about how nature works. At every step of the way, there's been significant technical challenges that take many people working for many years to make this happen. And I want to thank everyone who's helped me, the Michigan Kodo group. We have some members here in the audience. The Kodo collaboration, the Mu-to-E collaboration, and Eric Priebus for making the simulations. And particular here is the group of people that have been working here at Michigan. We have some things here to help you figure out this is Michigan. Stephanie's graduate student. She's just finished her thesis. He is a postdoc continuing to work with us. She is currently a second-year graduate student at Berkeley, first-year graduate student at UCLA. She's in her first year at MIT. Noah's graduating this spring and still has to decide whether he's going to MIT or Harvard, but he's going to take 2 years in the meantime because he won a Marshall Scholarship. She's going to have to decide between Wisconsin and UC Irvine and UC Davis and University of Chicago and University of Virginia and Michigan. She's been accepted to all those places. Monica's been working with me for a few decades now. He's having to decide between Michigan and University of West Virginia. Melissa's sitting right here in the front row, and she's still working on analysis of Kodo data. He's working at a software company here in Ann Arbor. And it has been such a pleasure to work with this group of people. Here is the entire Kodo collaboration, people working both from Japan and from the US. And here is the Mu-to-E collaboration standing in front of, you can see the experiment as a whole, standing in front of the pit where the experiment is going to go. So, thank you.